everyone, welcome back to the channel. So today in this video lecture we're going to be discussing about the problem detect cycle in a directed graph. So why I have included this problem in this series because in the next problems that we are going to discuss about topological sorting, they require the application of this concept, that is detecting a cycle in a directed graph. So if we have a directed graph, we got to check if there is a cycle or not, so that we can apply topological sorting in that graph, because only in directed acyclic graphs the topological sorting can be applied. So we must check if there is a cycle in the graph or not. Okay, so let's see how we can detect a cycle in a directed graph. So let's take an example. This is a directed graph which has 4 vertices numbered from 0 to 3, and I want to check if there is a cycle or not. So let's see that. We can see that there is a cycle like this. We go from 0 to 2, then we go from 2 to 3, then we move back to 0 like this. 0 2 3 0, right? There is a cycle. Okay, that means this is not an acyclic graph, rather it's a cyclic graph. So how can we detect it? So the thing that we have to keep track in mind is that, let's say we start from node number 1, we start from node number 0, we move to node number 2, then I move to node number 3, then I move back to node number 0. Okay, so there is a back edge. Here you can see there is a back edge from node number 3 to node number 0. So what is a back edge? A back edge basically nothing but when a node points to one of its ancestors from which it is coming. Like, we started from node number 0, we came to node number 2, then eventually we arrived at node number 3. Finally, we are again pointing from node number 3 to node number 0, which is the ancestor of node number 3, because we started from node number 0 and we came to node number 3. So it's an ancestor of node number 3, and we are coming back to node number 0, and hence this is a back edge. This is a back edge. Okay, so we have to detect this back edge in a given graph, in a given directed graph. How we can do that? Let's take an example. Okay, so let's take this graph. Let's take this graph. It has 5 vertices numbered from 0 to 4, and let's see if there is a cycle. So we can see that there is a cycle. Starts from node number 0, then we move to node number 1. Here you can see that from node 0 to 1, then from 1 to 3, then from 3 to 4, then from 4 to 0. There is a cycle like this. Okay, so let's see how we can detect it. We just want to detect if this package, we just want to reach this one, that is 0, because 4 points to 0 and 0 is one of the ancestors of 4. What are the ancestors of 4? 3, 1 and 0, and 4 is pointing to one of its ancestors, and that is 0. Hence there is a cycle. Okay, so let's see how we can detect the cycle. One of the solutions, the one of the thought process that one can think is just start from the very first node, that is node number 0, and just start doing a depth first search. Okay, perform depth first search from here. Let's take the DFS function, and it simply traverse the given graph in a recursive manner. So we start from node number 0, we call DFS function here, then it will recursively call the DFS function for node number 1. So let's say DFS 0 is called, then it will recursively call node number D itself for node number, then it will recursively call itself for node number 1, then eventually for node number 3, then for node number 4, and eventually from node number 4 we may move to node number 2 and then node number 3. Then from node number 4 I will traverse node number 0, DFS 0. Here I can see that I am revisiting this node. I am revisiting node number 0 because I started from this node. That means there is a cycle. I have detected a cycle. This is one of the tempting ways that one may come up with. So what is the problem with this approach? Let's see that. So I recursively call DFS2 for this node. Then we can see that from node number 2 we can't go to any other node, so we backtrack to node number 0. Then I traverse node number 1. I call DFS for node number 1. So this is the second case which I am discussing. Then from DFS 1 I will recursively call the same function for node number 3. So DFS3, DFS3. Then from DFS3 I may call DFS2, DFS2. Now DFS2 is already visited. We know we visited it here when I call this function for this when I call this function while traversing this edge. So it was called here. I am again calling it here. That means I will detect if I use plain DFS that there is a cycle, but we can see that there is no cycle. We don't have cycle like this. We want something like this, not this, here and this. Is this a cycle? No, it's not a cycle. So there is a problem. That's why plain DFS will not work for this case. We have to come up with another approach or a little modification. So for that, what I will do is, when I start traversing any node, what I am gonna do is I will keep track of path visited array. Okay, so I will keep track of the path which I have visited till now. How? I will use one more array, or like I will keep track of the function calls of the DFS which are there in the call stack. So we can see that, let's say we are here, we started DFS from node number 0. So what I did is I will take one more array, let's call it, okay, so let's call this recursion stack array. So what I'm gonna do is I'm gonna call this function for node number 0 and I'm gonna mark it as visited, because function DFS0 has been called. So this is present in the call stack. Okay, so let's take a call stack as well. So we just have to mark those nodes which are present in this call stack. Okay, so let's understand this using this example. We have this call stack. We call this DFS function from node number 0. This is my recursion stack array, and when we call this function for node number 0, this node comes into the call stack. Node number 0 comes into the call stack and we mark it as visited in this rec stack array. Then this will recursively call itself for node number 2. Okay, here for this one. Now that means this comes into the call stack. Node number 2 comes into the call stack and we mark it as visited. Fine. Now that's all. I will backtrack from this node now. From node number 2 I will backtrack because there is no node which I can go to from node number 2. So I will backtrack to node number 0. I will backtrack to node number 0. So this function call will be removed. Node number 2 will be removed from the call stack. So from node number 0 I will recursively call this node number 1. So when I remove this node number 2 from the call stack, I have to mark it as unvisited again. I will mark node number 2 as unvisited. So I will move to DFS node number 1. I will recursively call this function for node number 1. So it will come into the call stack. Then this will recursively call itself, and this I will mark as visited, and this will recursively call itself for node number 3. DFS3. 3 will be here in the call stack and I will mark it as 1. Then it will recursively call itself for DFS2. 2 will be there in the call stack and I will mark it as visited. Now from 2 I can go to nowhere. Now I didn't detect a cycle here. I didn't detect a cycle from node number 2. I can't go anywhere, so I will backtrack from here. That means I will backtrack from node number 2 to node number 3. So this will be removed and this will be removed. This will no longer be here and this will no longer be here. And node number 2 will be unvisited again because it is out of the call stack. It is not in the call stack now. So now I come to node number 3. From node number 3 I will recursively call itself for node number 4. But node number 2 is marked visited in the visited array. We have visited node number 2, 3, 1, 0. Okay, they are marked visited. So we have a visited array. Node number 0 will be visited, 1 is visited, 3 is visited, 2 is also visited. Okay, but this is the function calls or the nodes which are present in the call stack. We only have 0, 1 and 3 in the call stack. Okay, now from node number 3 I will recursively call itself for node number 4. Okay, so here that means it comes in the call stack, 4 is there in the call stack, and I mark it as visited here, I mark it as visited here. So here I'm saying that okay, the DFS call for node number 4 is present in the call stack. That's what I'm saying here. Then from node number 4 I will move to node number 0. DFS node number 0. But here I check that node number 0 is already there in the call stack. We already have 0 in the call stack. That means this 0 is one of the ancestors of node number 4. And that is indeed the case. We started from 0, we came to 1, we came to 3, then eventually we came to 4. Then again we have a back edge from 4 to 0. So this is a back edge. And I detect it over here because I see 1 is there in the call stack, and I return true from here. That means there is a cycle, so I return true from here. True, so this will return true, and finally I will have yes, true as the answer. That means there is a cycle in this graph. Okay, so that's all. That's what we have to do. We just have to declare two visited arrays. The first is usual visited array, which is used to mark the nodes which are visited, and the second is recursion stack array, which will keep track of the nodes which are there in the call stack. Okay, so whenever we call a function for any node, we got to mark that node into this recursion stack array, because the function call corresponding to that node is there in the call stack. That's what we are doing. Fine, so I hope you got the idea. Let's jump to the code. Let's jump to the pseudocode implementation. So this is my pseudocode implementation. Here is the isCycle function, which takes in this number of nodes in the graph, the adjacency list or the graph itself. We declare two arrays, visited array and stack recursion array. So this is used to mark the nodes to be visited or not. This is going to mark only those nodes which are present in the call stack. Then I initialize these arrays with 0 because initially all of the nodes of the graph are unvisited. Then I iterate over every node of the graph, and if I find any unvisited node, then I call the DFS function for that. Okay, so in this DFS function it is going to check if there is a cycle starting from that particular ith node. So I'm starting from every unvisited node. So I pass in the node, the graph, the visited array and the stack recursion array. Then if I find true, that if this function returns true, that means starting from node number I there is a cycle or there is a back edge, hence I return true. If I do not find my back edge or cycle while I perform this iteration, then finally at the end I will return true. So here in this DFS cycle I have this node, adjacency list, visited array, stack recursion array. I mark visited array to be 1, stack recursion array to be 1. Then that means they are visited. Node is visited and it is present in the call stack as well. Then I visit its neighbor nodes for the current node, and for all the neighbor nodes I recursively call itself. I recursively call this DFS function here. Okay. Otherwise, if the neighbor is already visited here, if it is visited, otherwise if it is visited, then I have to check if it is present in the stack recursion array or not. Because if I have a visited neighbor, that means it may be the case that we came from that node. It is one of our ancestors. If it is one of our ancestors, then that means the function call corresponding to this node must be present in the call stack, and hence if it is marked true, that means this is a back edge, hence we return true right from here. Okay, here. And this is basically, if we are just moving to the unvisited node, then we will recursively call that function. Now here, finally, after I iterate over all the neighbor nodes of the current node, I will mark this current node to be unvisited, because here I am backtracking. So while I'm backtracking, I have to remove this node from the call stack. And hence, if I remove this current node from the call stack, I have to mark it as unvisited or 0 in the stack recursion array, because I'm removing this function call from the stack. And finally, I will return false if I never return true from these two conditions. Fine, so that's how this function DFS cycle is working. And let's discuss the time and space complexity. We can see that we are just using depth first search, and for depth first search the time complexity will be linear, big of n, while we are using a stack recursion array that is going to take big of n space complexity. And that's all. This is the time complexity, this is the space complexity. Let's jump to the code implementation. So let's see the C++ implementation for the idea explained here. So let's create this function DFS cycles. So let's create this function which returns a boolean variable DFS cycle, which takes in the current node, the adjacency list, the array which is visited array, and the stack recursion array. Now I mark this node to be visited in this visited array and in the stack recursion array, because the function call corresponding to this node is there in the call stack. Then I will iterate over the neighbor nodes for the current node, that is, so if this current node is unvisited, then I will recursively call this function for that neighbor node. And if this returns true, then that means there is a cycle. Otherwise, I have to check if the neighbor is visited, then I have to check if it is there in the stack recursion array or if it is there in the call stack. So if it is there in the call stack, then that means I will return true. While at the end, I will remove this node from the call stack and I will return false at the end of this function. So in this fashion, this function is working, DFS cycle is working. Let's see how to implement the is cycle function. Okay, so in this is cycle function, we have the number of nodes, we have our adjacency list, we just declare two arrays or two vectors, that is visited and stack recursion, mark them to be 0. Okay, now iterate over all the nodes starting from node number 0 till node number n minus 1. Check if any node is not visited. If it is the case, then check if there is a cycle or not. If it is not visited, then start. So if it is not visited, then check if there is a cycle which starts from this node. If there is a cycle which starts from this node, from ith node, adjacency vector, visited array and stack recursion array. So if it is the case, then return true right from here. Otherwise, at the end, return false. Okay, so in this fashion, this function is working, and this is C++ implementation. Let's see the implementation in Java language. So let's create a class solution. Okay. Now in this solution class, let's create a function is cycle. So public static is cycle, which takes in the number of nodes, the adjacency list or array list of integers adj, and let's declare two arrays. The first array, let's declare the visited array which has size n. Let's declare the stack recursion array which has a size of n. Then let's iterate over the given nodes. Let's iterate over the, if I find any node to be unvisited, then I will call this function. Let's call it, so the second function is DFS cycle. The second function is DFS cycle. Okay, this is the second function, and I will check if this function where I pass in the given node, the adjacency list, the visited array, and this stack recursion array. So if this returns true, then I will return true from here, and at the end I'm gonna return false if I do not find any cycle. So here I will have this, I will create this function DFS cycle, public static DFS cycle. So let's define this function which takes in the node. So it will take a node, the array list or the graph, then a visited array, that is, so let's mark this current node to be visited in the visited array and in the stack recursion array. Okay, now iterate over the neighbor for this current node. Okay, now I have to check if this node, if the neighbor node is visited. So if it is unvisited, if it is not visited, then that means I will recursively call this function for this neighbor node. DFS cycle, pass in the neighbor, the adjacency list, the visited array, stack recursion array, and return true. Okay, otherwise check if this is already visited. So if it is already visited, that means if it is not visited, then recursively call this function. Otherwise, if it is already visited, then check if it is there in the call stack. So if it is there in the call stack, neighbor is there in the call stack, that means we have a cycle here. So we return true right from here. Okay, while at the end, if I do not find any cycle along this path, so I will mark this, and then I will pop this node out of the call stack, and hence I will mark this node to be unvisited, and I will return false at the end of this function because I didn't find a path which leads from this node. Okay, so in this fashion this function is working, and this is the implementation in Java. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to the channel and continue in this series. We'll be solving a lot of problems. Okay, where we will be using the topological sorting to find the solutions. So I hope to see you all in my next video.